Okay, good. Yes, your question. Here, let me throw you your candy.
On page 131,
I didn't bring the book. 131.
I guess I had a problem with G prime with plus or minus omega is 2 omega k.
All right, let me just see. Why don't you point to what it is that you're talking about? You mean y is g prime equal to that?
Is it different
We just differentiate.
with respect to?
G prime is this. The derivative is 2k0. K0 is omega, so it's 2 omega k. All right, any other questions? I bought a whole new box of candy the other day, so we're all set. All right, I want to get through as much of chapter 4 as possible because we're a little bit behind schedule. So first of all, we have these definitions and a couple of theorems about infinite series. So let me go over here. First of all, Sn is a sum n equals 0 to capital N Cn. Okay, so that's a partial sum. We say that the partial sum Sn converges to some number S if for any epsilon greater than 0 S sub n gets closer to S than epsilon for n greater than n of epsilon. I probably should have written this as a lowercase s sub n. So let's put it this way. In other words, if you go far enough out in the sequence, you get arbitrarily close to a particular limit. Now, if this is the case, then this is said to be the limit of the convergent infinite series. Okay, so that's the basic definition. And we say S is sum n equals 0 to infinity C sub n. Now, some series converge, some series oscillate and wander, some series diverge to plus or minus infinity. And I suppose some series go off, spiral out uncontrollably in the infinite complex plane. So they're real nightmare series. A series whose absolute values converge, the absolute value of the terms, n equals 0 to infinity. If this converges, then this series is said to converge absolutely. So a series converges absolutely if its absolute values converge. Examples, of course, 1 over n factorial converges to the number e, which is 2.718281828, and I don't know the rest of the series. On the other hand, the harmonic series, 1 over k equals, here we start with 1 for obvious reasons. So where you start a series doesn't always have to be 0. Although you can always call it 0, and you can then say that it's the series k goes from 0 to infinity, 1 over k plus 1. Anyway, this series diverges. This simply goes to infinity, as you can see by just writing it this way. 1 plus a half, plus a third, plus a quarter. And then you do 1/5 plus 1/8. And you see this is greater or equal to 1 plus a half plus a half, and so forth. So obviously this diverges. Now, it turns out, though, that this isn't a completely crazy series. It actually converges, it approaches the natural logarithm. So this series, k equals 1 to infinity, or I should say, k equals 1 to n of 1 over k is equal to natural log of n plus something called gamma. And gamma is the Euler-Mascheroni constant. And its value is about 0.57, well, 0.58 actually, so I better add another 7. Okay, now there are various tests of convergence. First of all is the Cauchy criterion. And what Cauchy noticed was that if you're given a series, you first of all don't know whether it converges or not, and secondly, you surely don't know what it converges to. And so this criterion here, which is the definition of convergence, this is kind of useless if you don't know what S is. Okay. So Cauchy invented a criterion that was equivalent to this, but that didn't require you to know what the sequence converged to. And his, so Cauchy's criterion is that the series converges if Sn minus Fm is less than epsilon for n and m both greater than some n of epsilon. So in other words, for any epsilon, if you go far enough out in the sequence, the partial sums are going to get very close to each other. It's easy to prove that if the series converges this way, then the Cauchy criterion is satisfied. Going the other way is more complicated, and it involves something called the Bolzano-Weierstrass theorem, which I might as well just mention to you. It's that if you have a bounded sequence, a bounded infinite sequence of numbers, then there's a subsequence that converges to something in this sense. But the reason why this definition applies to Cauchy's, of course, is that S sub n minus S sub m is less than or equal to S minus S sub n plus S sub m minus S, say. And you can make both of these less than 2 epsilon by this criterion. So it's easy to go one way. Going the other way is somewhat harder. There are various obvious comparison tests. Suppose we have a sum Bn, and all the Bn's are greater than or equal to 0. And we have some Cn, such that absolute value of Cn is less than or equal to Bn. Then the sum Cn converges, and in fact it converges absolutely, because obviously the criterion just involves the absolute values. It's also true that if you have if you have 0 less than or equal to Cn less than or equal to Bn, and here we might as well just say n greater than some big integer. It doesn't, because anything you say about an infinite series, you can always throw away the first 3,000 terms. They don't matter when it comes to questions of convergence. If the sum Cn diverges, so does the sum of the Bn. Well, it's kind of obvious. Okay, what's a little less obvious is that if you have a series, some Cn, and you can say that C sub n to the 1 over n is less than or equal to x, which is less than 1, then what you can say basically is that the absolute values of these things is up to some finite point, say, is less than or equal to some x to the n. And if x is less than 1, then you can sum this series. And in fact, this series actually sums to 1 over 1 minus x. This is called Cauchy's root test. Then there's a ratio test due to D'Alembert, and his criterion there is limit n goes to infinity, C sub n plus 1 over C sub n. Suppose that's R. Well, if R is less than 1, the series, then the sum Cn converges. If R is greater than 1, diverges. And so basically, it's kind of like the ratio. It's kind of getting back to this in a sense. It's saying that each term is smaller than the other one by a factor of R, and if R is less than 1, we've got convergence. Then in this modern world where we have very fast computers everywhere, you can just write a program in Fortran or C, or what I'm being told by some of my friends is that Python is the thing you guys really want to learn because it's so incredibly versatile. And so you write a program in Python to sum the first 1,000 terms, see what you get, then you do the first 10,000 terms, and the first 100,000 terms. And if the thing just sits there rock solid, you can be pretty sure it converges. And in fact, you know what it converges to. On the other hand, well, never mind about the other hand. I don't know what's on the other hand.
Is that the sit there test?
We also have MATLAB, and you can get MATLAB to sum some series.
No, I was just saying, is that the sit there test? If it freezes up,
all right.
Real quick, is the what if R is equal to 1?
I don't know. I mean, it's inconclusive. Oops, sorry. Okay, now we're talking about functions. So Sn of z, and z might be a complex number, is the sum Fn of z. So we sum a finite number of functions here. And we say this converges to S of z. Well, it's the same definition. Namely, that S of z minus Sn of z less than epsilon for, I keep using these capitals. Let me use lowercase. For n greater than some big N of epsilon. So if you can satisfy this criterion, then you say the sequence converges. Oh, hold it. I left out something. N in general depends upon z. So with this definition, we're just repeating the original definition of a convergent sequence. Because if you keep z fixed, this thing here is just, you can think of Cn as f sub n of z. And so you use the same criterion. On the other hand, you can have something much nicer if you can say that this is true for n greater than n of epsilon, which I originally wrote down by mistake. And this is if for example, z in some set. And what did I use? Do I use S for the set? What did I use? D. Okay. If some region of the real line or the complex plane such that whenever S is in that region, you get convergence where N doesn't depend upon Z. In other words, you get convergence for the whole set D. Then this is said to be uniform convergence. Okay. And if you have uniform convergence, then what you can say is that the limit of the integral of Sn of z dz, well, I was saying dx, so let's think simply in terms of a real variable, minus the integral s of x dx, that this is the same thing as the integral of, in other words, the limit, let me just give you the final result. The limit of the integral of the partial sums is the same thing as the integral of the limit function. And this is true as long as these things are uniformly convergent. So uniformly convergent on the interval. So we're talking about some interval here. On the closed interval AB, say, and that these things are also continuous functions. So if they're continuous on this closed interval, then they're certainly integrable, and you can then show that you can interchange basically the limit. So this is limit, n goes to infinity, the integral is a limiting process. This is the same thing as the integral AB of the limit n goes to infinity, Sn of x dx, which is the same thing as that. So that's an important result. Now, we say that a real function, f of x, is square integrable on an interval. This is what we were saying when we were talking about Fourier transforms. This thing is square, the function f is square integrable if it's absolute squared, is integrable and finite on a certain closed interval. And if you have a sequence of functions, and these are all square integrable. Some people use the phrase L2, meaning Lebesgue integral. The square is Lebesgue integrable. The advantage of saying L2 is that you don't have to write square hyphen integrable. You can just write L2. Okay, so if we have a sequence of partial sums, we say this converges in the mean. So the technical phrase is in the mean. Where they get these phrases, I don't know, but anyway, converges in the mean if the limit n goes to infinity of AB s of x minus Sn of x squared dx is 0. So this is called convergence in the mean. Sometimes one deals with convergence in the mean where one has a weight function rho that's non-negative, except possibly that's non-negative except at some isolated points where it might be zero. What I should say is that it's positive. It's always non-negative, and rho of x greater than zero except at isolated points. So that's another type of definition of convergence in the mean. It's where you replace 1 by rho of x. And of course, if the functions are real rather than complex, then in as much as you're taking a square, you can just use parentheses. All right, now there's a special class of series that is of particular importance, especially in the next chapter, and these are called power series. So let's just look at them briefly. Suppose S of z, and let's think of z as being complex. Suppose f of S of z is a sum Cn z to the n. So what we're saying here is that Fn of z is C sub n z to the n. So we're saying that Fn is a special kind of function. And now we're talking 0 to infinity. So this is said to be a power series. It's not the same as a power lunch. It's a power series. And the idea is that you have increasing powers of z. Now, if we use the ratio test, what we're looking at is limit n goes to infinity, c sub n plus 1, but now it's z to the n plus 1 over cn z to the n. And so you see this is the limit n goes to infinity of simply c sub n plus 1 over c sub n, but out in front we can pull the absolute value of z, because there's an extra z in the numerator. And so the question is, what is this? And if we call this thing 1 over r, then we can say this is z over r. Well, if this is less than 1, then we have convergence. And so what we've got is that power series converge inside disks of radius r, and r is defined by this criterion here. 1 over r is the limit n goes to infinity cn plus 1 over cn. So that's the story there. Yeah. And within that series, within that circle, because we've been talking about absolute values, the convergence is absolute, because we've only been talking about absolute values. And secondly, it's uniform, because if it converges on the circle, it surely converges inside the circle. And so that's how that works. Now, these power series, of course, are very, very important. Taylor series expansions and analytic functions just generically possess power series expansions, and so these are play a big role in mathematics. One example is a geometric series, and should pay attention to this example because it's super useful. 1 minus z, 1 plus z squared plus dot 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 plus z to the n. Well, if you multiply that out, you take 1 times all of that, you get that. Then you take minus z times that, you get minus all of this. And except for one term that's left over. And so you can convince yourself that this identity is true. Well, this has a remarkable consequence, because it means that S sub n of z which is the sum z to the n up to n from 0, is 1 minus z to the n plus 1 divided by 1 minus z. And so consequently, as if the absolute value of z is less than 1, then this thing converges to 1 over 1 minus z. So that's the statement that this power series, z to the n, just converges to 1 over 1 minus z, as long as z is less than 1 in absolute value. And that's very important, and there are just many cases where this identity is useful. All right, I think I'll leave that alone. And one example of the utility of this thing is that you can say if you have 1 over 1 plus or minus z, this is approximately 1 minus or plus z for z much less than 1. So you often you'll be doing a physics problem, you can factor something out and you got 1 over 1 plus or minus something that's small, or you can always rewrite it this way, approximately. And so that's quite useful. Let me do the credit example. In case any of you wants to branch out into economics, I think actually the country would be a lot better off if more economists had a background in physics. So I'm all for PhD physicists entering the field of economics. Because there are an awful lot of economists who, I mean, they're just hopeless. And let me just tell you why you might want to switch into economics. A friend of mine at Brown University told me that at Brown, the professors who are paid the most are those in the Department of Economics. Because it makes sense, because that's, closest to money. And so you've obviously, I guess the professors in that department go to the dean every few months and say that they're thinking of leaving to work for a certain bank and the salary goes up. All right, anyway, so just to get you started on your careers in economics, let me just mention something about credit. So suppose somebody deposits $100 in the bank. Or a credit union. By the way, credit unions in general treat you better than banks. So occasionally they screw up, but if they screw up, they'll make you whole. Once they figure it out, they'll apologize and fix it. But there's banks around to screw us all. All right, so you deposit $100 in the bank. This guy has credit of $100. That is, he can write checks for $100. And suppose banks have to hold 10% of deposits as reserve to avoid financial crisis. So they lend out, so this original bank lends out 90 to another depositor, to a borrower, I should say. And then this borrower, having the 90, can deposit it in another bank. And that bank then can lend 81 to a third party. So at this point, we've got 3 people with credit. One has a credit of $100 because he deposited it in the first bank. The second guy has credit of $90, and the third one has credit of 81. And so altogether, we've got credit. There's $271 floating around that can be spent. And that multiplication money, that's called the miracle of credit. And if in particular P is the original deposit and R is the fraction for reserves, then the total credit is P plus P times 1 minus R plus P times 1 minus R squared and so forth. And this is P sum 1 minus R to the n. So this is P over 1 minus R. And this is just P over R. So if R is 10%, 0.1 in other words, then the total credit is, then $100 produces $1,000 of credit. If on the other hand the reserve requirements are 1% instead of 10%, then this goes to 10,000. And now the banks, of course, are lending all this money to various borrowers and charging interest rates. And so you can see from this that there are two things that banks love and will argue for on talk shows. They love no regulation, so you send R down from 0.1 down to 0.01 or 0.001. And secondly, that you let interest rates go up, because then they are lending out all this money and they're charging whatever they choose to charge, whatever they can get away with as interest rates. And so if you have been listening to financial news for the last, since the financial crisis, you'll hear Ben Bernanke and Janet Yellen, who are saints, essentially, as well as being very smart. They keep keeping interest rates at zero to get the economy out of the ICU. And on the other hand, all the people representing the banks are saying, well, it's important to get interest rates up. It's important to go back to a normal level of interest rates. And of course, that's so the banks can make a lot of money. Okay, sorry for that. But now you can all make a fortune as economists. Let me get another piece of chalk here. So the next topic is something that's technical, but very important. And so let's just do it. I mean, most of it you already know. Namely, you know that n factorial is just n minus 1, blah, 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 3, 2, 1. This is if n is a positive integer. The convention is that 0 factorial is just defined to be 1. There are various estimates for n factorial. The one that everybody knows, and the simplest one, is Stirling's rule, 2 pi n, square root of 2 pi n, and it's quite curious. It's n over e to the n. So it's a, when you look at that and you say to yourself, my God, where did that come from? And Ramanujan, an Indian mathematician, gave this as a correction, 1 plus 1 over 2n plus 1 over 8n squared to the 1/6. And you might say, my God, where did that come from? But then, oh, by the way, with regard to this man, this Indian, I asked Subhakar Prasad how he actually died. And what he said was that Ramanujan was a vegetarian, and of course food in England has always been miserable, but especially inedible is the vegetarian side of or the vegetable side of the British cuisine. And so Ramanujan was just was malnourished in England, and he was subjected to the cold of the English and the dampness of the English winter, and so he had his immune system. He was malnourished, and he got TB, and his immune system couldn't fight it, and he died. Anyway, Mermin has gone beyond Ramanujan's correction, and what he did was he wrote down an infinite product formula that's exact. That's n factorial equals, and it starts out as Stirling's root 2 pi n over epsilon to the n, but now it's product j equals 1 to infinity, 1 plus 1 over j to the j plus a half, and all of this over e. So that's that, and now that it turns out is exact. And he then has approximations to this. His first approximation is root 2 pi n over e to the n, e to the 1 over 12n. And that's very easy to implement because you just throw in an exponential and bingo, it's a lot better. If you go beyond that, the second approximation is minus 1 over 360 n cubed plus 1 over 1260 n to the fifth. So that's the next approximation. And in figure 4.1, I've graphed the difference between this and n factorial divided by n factorial. And it turns out that Mermin's second approximation is really accurate. That's funny. I'm just wondering if I've plotted this thing backwards, because I would think that the error would go up with big N, but apparently not. All right, anyway, so for its... Anyway, let me just tell you what the accuracy is. On this graph in the figure, Stirling's is just off chart. Mermin's second approximation is the most accurate of the three. The next most accurate is Ramanujan's formula, and then this one is Mermin's first approximation. So his first, his second, Ramanujan, and this is the error. The relative error times 10 to the 8th. So that's to make it. Okay. All right, let's go on from there. I was once on a bus, by the way, at a conference, and the bus was taking us from a conference hotel or something. And I heard behind me two people talking, and gosh, one of those guys was really smart. Turned out to be Mermin. All right, so what is this? This is just defined to be n factorial, k factorial, n minus k factorial. So this is the binomial coefficient. And of course, it's used everywhere. It's really important. There's even a LaTeX formula for it. It's something like /choose, and I guess curly brackets, n comma k curly bracket, something like that. All right, an example of this, of the utility of this, is Leibniz's rule. Suppose we define the derivative, take the nth derivative of f of x times g of x, product of two. Well, this is a sum, k equals 0 to infinity, nk, the kth derivative of f of x, and the n minus k derivative of g of x. So that's Leibniz's formula. One of the things you can notice is that, when I was a student, first heard that Leibniz and Newton had invented calculus, I imagined that as far as they got was maybe differentiating x to the 4th or something, because they had just invented calculus. But you see, they were doing very non-trivial things with calculus. They didn't just invent it, they developed it. We'll see later that if you have something like a plus b to some power n, it's a sum k equals 0 to n of nk, a to the k, b to the n minus k. So that's one reason why it's called the binomial coefficient. Okay, well, factorials obviously occur in exponential functions, and the exponential function, of course, e to the z, it's a sum z to the n over n factorial, and if you apply the ratio test to this, you see that you get as r, or as, what you get as r is the limit 1 over n plus 1 inverse as n goes to infinity, and so r is infinity, so it converges everywhere. Then the Bessel function, the standard Bessel function, Jn of rho, it has 2 factorials. It's a sum with 2 factorials. I don't think you can write it like that. It's 4.49, and so it converges even faster than the exponential function. Double factorials. Well, these are useful, and it's easy to define them. But of course, you have to know what the definitions are. 2n minus 1. So if it's an odd factorial, then what you get is 2n minus 1, 2n minus 3, dot, 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 down to 1. On the other hand, if it's 2n double factorial, what you get is 2n minus 2, dot, 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 down to 2. Now, there are 2 double factorials that have to be defined by convention, and both of these are 1. And so you might say, well, we already said 0 factorial was 1, so I guess 0 double factorial can be 1. Why minus 1 double factorial is 1 might be puzzling, but that is the convention. And I think we'll just leave it like that. Okay, the next thing is, this is what's really important, this business about these various approximations to n factorial. These are things that, well, the n factorial, you always knew Stirling's formula, I think. So this other stuff is, these are better than Stirling's formula. Let me just mention, though, if we can turn the thing a little bit, one of the problems with factorials is that they get big very, very fast. And so if you're doing a numerical calculation on a computer, you can very easily get NaN as the answer to your calculation. And of course, NaN means not a number. The reason is they just go just absolutely fast. So what you have to do is you have to use some other approximation to cope with these very, very large numbers. You just have to think about what your problem is and avoid using anything like 50 factorial because it's just gonna, it's just hopeless. Okay, now, here is a generalization of the factorial from integers to complex numbers. And it's integral 0 to infinity, e to the minus t, t to the z, dt. And where does this work? Well, we're talking real z greater than minus 1. So, and the reason why we want real z greater than minus 1 is that we want to be able to do this integral near t equals 0. The big T part of the integral is no problem because you've got an exponential here. And if we then go to 0 factorial, well, this is integral 0 to infinity e to the minus t. T to the 0 causes 1, so this is just dt. And that's obviously 1. So now you see why 0 factorial is 1. The z minus 1 factorial is something that is called the gamma function, gamma of z. And for real, so for reals, now we want real z greater than 0. And this gives us integral 0 to infinity e to the minus t, and now this is t to the z minus 1 dt. So that's the gamma function, written as a capital Greek gamma. And we can see if real z is greater than 0, then this exponential is like t to the minus 1/2. You can integrate that. Okay. And what we can also do is we can do this. This is simply an integration by parts, but if we write down what gamma of z plus 1 is, well, if you said z to the z plus 1, you just get t to the z there. So that's 0 to infinity, e to the minus t, t to the z dt. And now you can write that as minus d by dt of e to the minus t, t to the z dt, obviously. But now you can integrate by parts, and the surface term at infinity is clearly 0 because you have e to the minus t. The surface term at t equals 0, well, as long as real z is greater than 0, there's no problem. And so what we do is we get integral 0 to infinity e to the t minus t d by dt of t to the z dt. And this, of course, is easy to differentiate. You just get t to the z minus 1. So that's e to the minus t z t to the z minus 1 dt. And that is just z gamma of z. So that's the remarkable relation. The thing that's really, really important. This is z gamma of z. Again, if real z is greater than 0, this works. And so what you can do is you can sort of invert this. You can say, well, gamma of z then is gamma of z plus 1 over z. And this works if real z is greater than 0. But now we can do the same trick, and all we need is real z greater than minus 1. And because the next thing we're going to do is we have 1 over z plus 1, gamma of z plus 2. And then pretty soon we have 1 over z plus 1, z plus 2, ... And if we're just at z plus 2, then, well, it's gamma of z plus 3. So let me not have ... Anyway, this allows us, you see, originally this definition only worked for real z greater than -1, or if we're doing it this way, real z greater than 0 was our original definition of gamma of z. But now as we do this, we see it's 1 over these things, gamma of z plus 3. But this is okay as long as z is greater than -3. So what we've done in this way is extended the gamma function from the right half plane back to greater than -3, the half plane greater than -3, except for these points, z equals 0, z equals -1, and z equals -2. These things are called poles, and we'll learn more about them next week. This is called analytic continuation, and it's in fact probably the most important example of analytic continuation. Mathematicians talk a lot about analytic continuation, but frankly, this is almost the only example that comes to my mind easily. All right, anyway, Euler took this and came to a remarkable formula for gamma of z. Namely, gamma of z is the limit n goes to infinity of, well, that's n factorial on top, and on bottom it's z plus 1, z plus n, and then n to the z. So that's Euler's formula. Weierstrass had something even more remarkable. E to the minus gamma, and this gamma is this 0.577 dot dot dot, the Euler-Mascheroni constant, divided by z, and then this infinite product. And as I said to you maybe last week, I don't know when it was, these infinite product formulas strike me as almost magical. Okay, so that all is in the denominator actually. So it's this infinite product formula that's really quite remarkable. There's something, well, all right, never mind. There are is there a question? Yeah.
Are those T's or C's?
I'm sorry, say it again.
In the book you have Z's. There's no T's. Or is that those are Z's?
These are all Z's.
Okay.
What does the book say?
It says Z. I was looking on the board. It looked like a T. My fault. Here.
Well, yeah, you know, if you look at this, I was looking at it's particularly if you look at this from this side, it does look more like a T.
It's more on the E to the minus.
You look at it straight from here, right here.
That's good. There's a gamma Z.
Yeah, that looks a little better. Okay. All right. There are several. Well, hard here. Let me just give you another formula for gamma of z. Another expression is gamma of z is 2, 0 to infinity, e to the minus t squared, t to the 2z minus 1 tt. Okay, so that's that formula might be more useful if you're doing things analytically, because that e to the minus t squared is going to converge like nobody's business. All right, anyway, I'm going to skip the next two equations, which are just formulas for gamma of n plus a half. Those are two formulas. Actually, maybe I should write them down because there was a typo in the one version of one edition of the book. So gamma of n plus a half is 2n factorial over n factorial 2 to the 2n square root of pi And another formula for that is 2n minus 1 double factorial over 2 to the n square root of pi. Obviously, the second one is simpler. So these are two formulas there. Now, once, if we go back to the original, the original definition of the Bessel function, you see that the Bessel function had 2 factorials in it. Yes.
You just addressed my question. My question
All right.
is,
Well, let me just say something. Let me just.
what double factorial is?
Jason.
That was, is that what you were going to say? What the double factorial is?
We weren't defined double factorial
Oh, okay.
for integers. J sub rho, all right, let me just say what it is. It's rho over 2 to the n, sum on m, 0 to infinity, minus 1 to the m over m factorial, m plus n factorial, rho over 2 to the 2m. Okay. This is minus 1. Now, once we know how to generalize n and m factorial from integer to complex numbers, you see, this n, which was an integer originally, and had to be an integer because we had a factorial here, once we know how to do this in terms of gamma functions, we can define J nu. And say, so J nu of rho is rho over 2 now to the power nu. Nu is just in non-integral values. In fact, they could probably be complex. Sum minus 1 to the m again, m factorial, but now we have gamma of m plus nu plus 1, and then rho over 2 to the 2m. So the part involving m doesn't change, but the part involving n changes, and we get a gamma function here and a nu here. And so that's well defined, at least in principle, for arbitrary complex nu. The spherical Bessel functions, you may, when you first hear about Bessel functions, there are 2 kinds, well, there are several kinds, but there are cylindrical ones and spherical ones. The spherical ones have more symmetry, and they're very simple functions. The cylindrical ones have less symmetry, they're pretty complicated functions. You can see there's just nothing trivial about that. It's an infinite series, these factorials, minus signs, you name it, it's there. And so it's complicated. But the spherical Bessel functions are quite a bit simpler. And we'll talk about them when we get there. I think I'll just skip that. Now, a Taylor series, of course, you heard about Taylor series when you first studied calculus. It's f of x plus a f prime of x plus a squared over 2 f double prime of x plus dot dot dot, and then plus a to the n minus 1 over n minus 1 factorial f the n minus first derivative at x, and then plus a remainder e sub n. And it turns out that you can bound e sub n. E sub n is actually equal to a to the n over n factorial, the nth derivative at some point x plus y, where y is less than or equal to a and greater than or equal to 0. So in other words, you get the exact answer if you just stop and you pick the right value of y between 0 and a. Curiously. In quantum mechanics, of course, we make use of these Taylor series a lot. And in particular, we would write this Fourier series this way. F of x plus a as a sum avn over n factorial fn at x, and we'll write that as e to the a d by dx on f of x. And now in quantum mechanics, we just got to stick in an I and an H bar, an I to make something something else for mission, and so we'll write this as e to the IAP over H bar f of x, where p is H bar over I d by dx. So you can see that the relationship between d by dx and translations is this way. And what's, as I said, I may have said in this course, the essence of quantum mechanics is that, or close to the essence of quantum mechanics, is that the momentum operator, P, implements translations. And that's what really distinguishes one from the other. We can think of Fourier series as power series. And for instance, we can say f of x, of course, the Fourier series is we're summing from minus infinity to plus infinity, Cn e to the I 2 pi n x over L over the square root of L. And the coefficients, of course, are integral minus L over 2 e to the minus I 2 pi n x over L over the square root of L. F of x dx. And so we can say this is actually a pair of series, 1 over square root of L, sum Cn z to the n from 0 to infinity, plus sum 1 to infinity C minus n, Z inverse to the n. So that's writing it somewhat perversely. And so these are power series in Z and in Z inverse. And these are going to have inverse radii of convergence, which are limit n goes to infinity, Cn plus 1 over Cn, where these are the Cn's. And R minus inverse, again limit, n goes to infinity, absolute value C minus n minus 1 over C minus n. And in particular, then, these power series then will converge uniformly and absolutely as long as, in the first case, Z is less than R plus, and in the second case, 1 over Z is less than R minus. And this Fourier series 470, well, absolute value of Z, of course, is 1 in these cases. And so we get the convergence as long as R minus inverse is less than 1, less than R plus. So the question is, so we've got the convergence in this case. And so I don't know, I give an example of that, but I think we can skip it. We are again running out of Blackboard space. there any questions? Maybe, no, all right. Let's just look at the Taylor, particular Taylor series then. 1 plus x to the a, say. Now, if a is an integer, that's a pretty simple thing. It terminates. But otherwise, it's sum n equals 0 to infinity x to the n over n factorial. This is the Taylor series. dn dx to the n 1 plus x to the a at x equals 0. And what that turns out to be, if I skip an intermediate step, is a sum n equals 1 to infinity a minus 1, a minus n plus 1, n factorial, x to the n. So that's the series. If a is a positive integer, then what we have is the binomial series, namely 1 plus x to some power n. It's just the sum nn x to the n. And other relations are x plus y to the a is y to the a plus this sum very much like that, n equals 1 to infinity a minus 1, a minus n plus 1, n factorial, x to the n, y to the a minus n. So that's an infinite series, and of course, if the thing is a binomial series, and let me just stick a y in here, this will be y to the n minus n, and that gives us binomial. These binomial relations are often useful. I'm going to skip the next two examples. You can read them, but let's go now to a particular series, logarithmic series, natural log of 1 plus x. Well, of course, it's an example of x to the n over n factorial dn dx to the n of log of 1 plus x, again at x equals 0. And if we carry out those differentiations, what we find is a pretty simple series. The log of 1 plus x is a sum from 1 to infinity of minus 1 to the n minus 1, x to the n over n. And that converges slowly. And of course, the reason it converges slowly is it's just this 1 over n. The remarkable thing is that, and let me just separate it for you, because you see, it converges even if x is big. And the reason it converges is these alternating minus signs. But because it's just 1 over n, that's pretty slow. Actually, when I said it converges for x big, it's not true. This converges for x less than or equal to 1 greater than minus 1. So I misspoke when I said it converged in that. There are two other formulas that are useful. So let me just write down. These are things that should know about in the sense that, of course, you just look them up. I mean, you can just Google them or something. Minus a half x squared plus x cubed over 3 plus dot dot dot. And log of 1 minus x is actually simpler. It's minus the sum from 1 to infinity of x to the n over n. So that's a very simple expression. And then the ratio, log 1 plus x, 1 minus x, is 2 times the sum from 0 to infinity of, I have to write it here, x to the 2n plus 1 over 2n plus 1 because I wanted to get that out of the way. So that's that point, yeah.
How would we show that that thing converges if you wanted to show it? Because the root test, the root test wouldn't work because
Yeah. Well, you know, I mean, these various, there are a whole panoply of tests. Okay. And some of them work for some series, not for other series. And, you know, but in this modern age, just, you know, write a Python program or a Fortran program, or pull up MATLAB and solve it again.
But with that, suppose you do that. You watch the series for arbitrarily large values of terms you're including.
Yeah.
If it's not slowing down, you can't necessarily conclude that that it won't at some point in the future level off and converge. If it looks like it's not converging,
Yeah.
right? Especially something like
All
that.
right,
which
look,
converges linearly.
I mean,
I don't know. I was messing
all right,
around. with it.
I mean, there are other tests that I didn't go through because, they get complicated, and the proofs of these tests are even more complicated than the tests, much more complicated than the tests. And it gets very technical, and it probably doesn't answer your question anyway, because there'll be series that don't, you know, that you don't resolve with those tests. Okay, now, Keith Sanders is putting the homework in the boxes for the people who have boxes, but he's also going to bring some of them here for the people who don't have boxes, or if he couldn't find the box or something. Well, there's sometimes in the future, on your homework, print your name. In fact, it would even be better to print your name in block capital letters, because, you know, these last names, if you just write it in script, I mean, you know what it is, but nobody else does. All right, well, let's take a break. The problem set will start in 13 minutes or so, so you're going to stop this, right?